I forgot to press record too, so it's recording now. Yeah, I think we're gonna... So I think it makes sense to do those dual batteries instead. And we might have to redo a few things, calculations, but that's fine. I think one other thing too I want to knock out real quick. I don't think I finished adding all of the parts to the schematic that I have here. And also I forgot what this is about. What is this part? Oh, that's the 555 timer. Okay. I knew that. So, yeah. I think I added all of these parts. Yeah. 2R1, that's all in here. R47, R49. Yep. So I think it's just on this page, on the battery connectors. I didn't add these diodes. So I want to do that first. So let's just grab this part number. Oh, 6 amp. Is that what this is? If so, this won't be a... If it's a 6 amp diode, this will not be a problem at all. To just replace a couple of the battery circuits. Average current rectified 2 amps. Forward voltage drop at 2 amps is 1.1 volts. I don't think that's the max it can do, but that's probably... Oh, maybe it is. Oh, hold on. Oh. It has a couple of numbers in the... It has an IFSM. Hold on, what is that? Diode FSM. What does that mean? Okay, so IFSM is the maximum surge, or maximum forward current. Forward surge maximum is what it is. Okay, that makes sense. So the maximum peak current. So, and it says 35 amps for that, which is insane. I don't think we have to worry too much about these. So, yeah. So I think this plan makes sense. I think we get rid of... I guess I got to decide at this point. Do we get rid of half of this? Or do we leave it in and just not populate it in hopes that we can avoid having to use it? I don't think that option makes much sense. I think it makes more sense to just get rid of it. That'll simplify the schematic too. All right. Let me get rid of it. Actually, what happened here? All right. I need to add these diodes to the bill of materials. D2 through D5. Do I have a D1? I do. Up here. Okay. But I'll have D2 through D5. Just don't think I do. If anyone sees it, let me know. can't wait to spend all the money to buy this and end up giving DigiKey like $1,000. That was my guess for how much the parts were going to cost, but I honestly don't know. It's not going to be cheap, but it may not be as expensive as I'm thinking it is. Problem is, some of the stuff is like super cheap, and some of it's like costs a little bit, like $1 or $2, but that all adds up when you're buying so many of them. All right. Okay. So the tricky part is with removing this, I need to remove them from the bill of materials as well. So J1 through J8 is going to become through J4. And then D5 and D4 are going to be gone, so it's going to be D2 through D3 left. Okay. Now let's see what happens when I do this. I'm hopeful that this just ends up making the schematic look, or not the schematic, but the layout look so much better. Let's see. All right, so that's good. And then for the chargers, we got to remove these. And we can remove these charge status pins. So let me do that here on our pinout. And actually, let me get rid of them on the teensy first. So for 2 and 3, hold on, that was connected there. Okay. So make sure I get all this right again. All right. This will make it easier too, because we don't have to keep track of 2 batteries, and this gives us a couple extra I/O for other things. I still have no idea what this little line down here is. Okay. So that's good. Battery connectors are good. Power supply doesn't change because it's same charging circuit for everything. Well, not the same charge, same booster and regulator. And the chargers, we got to get rid of all of this. So I guess I just got to start going through the list. Okay, so 43, 44, 45, 46. That's probably gonna. Yep, so just through 42. This is going to be a bit of a process, but to make sure I got everything lined up, I'm going to delete these one at a time. All right, C 33, 32, 32, 33, 35, 36. We leave 34. All right, so 32, 33, 36, 35. All gone. Okay, R37 and 36. 36, 37, 39, 40. We leave 38. Where is that? Are these weird values? Oh, here they are, 34 to 37. $35, $34, $35. So there's 36 and 37. Okay. Q21 and 22. It's kind of a shame to do all this design work on these and then delete them. But this happens more often than you would think. Part of engineering is iterating through the design, and if you realize halfway through that you could do something better, then typically you want to do that. Not always. Sometimes you're too far into a design and you have to commit to something because the amount of time it would take to rework it would negate the value you'd get from just finishing it. You can see that kind of stuff in cell phones or iterative types of devices where they release a new one every year. They may decide that they want to do something like add a new fingerprint sensor or something, and then, oh, well, that would be too hard to do. Let's do it on next year's model kind of thing. All right. 51, 52, 49, 48, 51, 52. So 51, I got 51, 52, then 49 and 48. All right, get those. And that's all the components, and then we just have these U11, U12. And with that, we can delete all of this. All right. That cleans that up a bunch, doesn't it? All right, so let's validate all of this and send it to the circuit board. If we look at this, I want to look at this before and after. Here's all of our components. Now let's go back here, update PCB document. Sure, whatever. Validate. It'll have some issues, probably. Oh, I can't add this because of nothing connected to it. Okay, that's fine. Somehow it did. Interesting. All right, a bunch of stuff got removed. There's still a lot there, obviously, but like in here you can tell a bunch of components got taken out. So that's good. That's really good, actually. Okay. So I think that gets us up to date. Everything is up to date with the bill of materials now. And all this is good to go. So next thing. Well, here, let's save this. And then I'm actually going to save all this to the server. Just back everything up. Also, if anyone remembers, I'm still actually working on the MIDI controller project. I've run out of money, so I gotta wait a little bit. But I'm gonna get a better cutting tool and finish that up. That's still on schedule, or it's not on schedule. It's on the schedule, but it is definitely behind schedule. Oh, looks like our little 555 timer got added. That's fun. Anyways, though, I will finish that at some point. I'll probably finish it off stream, just because that's tricky to work with and film at the same time. All right. So we're going to use these. There is a fly. All right. Assembly. Did I add these in here? No, I did not. Probably need to add these in here. Three, 5, 4. We'll look these up on DigiKey, and then we'll add them to our bill of materials here. I wonder if they're in stock even. Yes, they are. Sweet. Check this out. 390 of them. And they're same price, 20 bucks. So that works. 4.4 amp hours. An insane amount, if there ever was one. All right, there we go. Okay, so now the next thing, even harder. Don't need this anymore. Here, we need to add a battery balancing circuit using capacitors. I found an article that has a lot of equations that explains kind of what's going on here, but I don't understand it super well, nor do I know if it's totally true. It's just an article of the design considerations. A really specific article, though. Capacitor sizing, balancing, and pre-charge for flying capacitor boosters. This sounds really like a really useful read. So I want to go through and kind of figure this out. Okay, so this is going to be a lot of reading. I apologize if I go kind of quiet here. I'm going to be trying to understand a lot, but I'll be talking through it as I go, because that usually helps me figure out what I'm doing better and understand something better. But if you have questions or feedback or thoughts, please interrupt me and let me know. Asking questions helps me explain things to understand them better, and any kind of feedback will give me other things to consider, stuff that I might be missing. All right, so yada yada. The article, second part of the series about flying capacitor boosters, the energy operation of flying capacitor boosters, but let's not. Describe the advantage of it, which is increasing the efficiency while still being low at system cost. The second part focuses on the challenges of the flying capacitor may occur. Solutions to tackle capacitor sizing, balancing, and pre-charge are introduced here. Using high efficiency solar inverters is increase efficiency while still being cost efficient. So that's one thing I was confused about. Size, balancing. I'm not sure what exactly it means by that, and or pre-charge, what that means either. So hopefully this will explain. All right, so first thing, the size. The voltage supplied by a flying capacitor has a key role in this technology. Key voltage ripple on the capacitor low, a suitable capacitor size is needed. To determine the needed capacitance, the switching frequency and the maximum allowed voltage ripple need to be considered. The size of the capacitance can be calculated as capacitance equals the peak current over the maximum allowed voltage ripple times the switching frequency times 2 times the switching frequency of the transistors. So this relies on knowing how fast the transistors are flipping back and forth too. This makes some amount of sense because, okay, so let's try to understand what happens here. If the peak current allowed is higher, then you can go for a bigger capacitor, because a bigger capacitor will hold more charge and have a higher current as it dissipates. Okay. If the maximum allowed voltage ripple is greater, then that makes for a smaller capacitor. Why? I don't think I understand what voltage ripple is. At least the way they're describing it. Allowed ripple. Hold on. I'm assuming voltage ripple is just like a change in voltage that will occur. Like a spike, basically, right? Like if you have a high capacitance come in, if you have so this system is a battery, which is kind of like a capacitor, sort of, a very loose form of the word. And if you have a capacitor that has a very high voltage come in, then there's going to be a spike in voltage briefly until everything settles out. And I'm assuming that's what this is. What I don't get is a larger allowable spike makes for a bigger or a smaller capacitor. That's counterintuitive to me, because you would think a bigger capacitor would cause a bigger spike. It doesn't help that they're missing their symbols from this sentence right here, where blank is the maximum allowed voltage ripple. I'm just kind of guessing based on the terminology. Like maximum current, I is current, and peaked. Okay, that makes sense for maximum. Switching frequency, the frequency of the switch. So by process of elimination. I'm looking up what a farad is, because I feel like that might have some. This obviously has to calculate down to capacitance, which is in farads. So these units have to work out. So this is current, which is amperes, over a frequency. Frequency is 1 over the period. And period is in seconds. So frequency is 1 over S. I wish I had a way to write this out for you to understand what the heck is going on here, to make sure I'm calculating this right. That way I can know the units that this is. This apparently is a change in capacitance. Is a change in capacitance just voltage? Gonna teach myself a lot here accidentally. Oh wow. Wikipedia article has the Faraday has a lot of different equations that you can use for it. This one's really interesting. Amps times seconds over volts, and we know that the frequency is 1 over seconds. So when you divide by a fraction, you multiply by there's the flip it and multiply by reciprocal. Is that it? Maybe. Which would make it multiply by s seconds. So this is the one right here that it's equal to. Amps times seconds divided by voltage. So ripple is just in volts. So I'm assuming that's the maximum change in volts that's allowed. All right, so I'm going to skip this for a moment, but I think I have an understanding of what's going on. I don't understand the theory behind it. Like, I understand the math, but that just doesn't compute for me. Why? Like, a smaller change in voltage makes for a bigger capacitor. Or maybe a bigger capacitor absorbs it better. Like, less of a spike. Oh, that might make sense, actually. The frequency part makes sense. If it's going faster and that's higher, then you need a smaller capacitor because a big one will cause a bigger, like, jolt in the system. There's some counterintuitive things going on here. Okay. For the appropriate operation of flying capacitor, voltage has to be half of the output voltage. To achieve this, it must be regulated at all times. This can be done by changing operation modes. As it can be seen in Table 1, Mode 1 and Mode 4 have no effect for the flying capacitor. So for regulation, Mode 2 and Mode 3 have to be used. The regulation state diagram can be seen. I need like a diagram of the circuit here. Do they have a picture of it? They give values here, T25, T27. What are those in reference to? Here we go. Okay. Oh, okay, so this is our flying capacitor. And I'm assuming the C out 1, C out 2 is like our representative of our batteries. So we're going to need like diodes and whatnot going on here, and an inductor and DC link voltage, FC voltage, that's the flying capacitor voltage. All right. If the flying capacitor voltage exceeds the set point, the operation can be modified to decrease the voltage. 3, mode 1, mode 3 is less than the set point. Okay. So you have to sense the voltage of the flying capacitor. It's just basically, this is a diagram to tell you how you should switch things. I just don't understand totally the link that is happening here. Okay. This section describes the details of the method proposed by Mitsubishi Electric to protect the flying capacitor booster when there are no control signals. In case when all control signals of transistors are low, the flying capacitor cannot be regulated. In that operation, an extra effort is needed to keep voltage on the safe side, failing to eliminate the overvoltage on the center may cause fatal error in the system. There are 2 operation modes. When all the transistors are off, when input is applied and output is equal to the input startup, and when input is 0 and the output is not. This happens, for example, when the voltage of the center is below the breakdown voltage, additional balancing has to be used. Current flows through the 2 diodes and charge the output capacitance. In this case, the output voltage is equal to the input voltage, while the flying capacitor voltage is 0. Huh. Oh, this is some sort of... Okay, hold on. There's something different going on here than I was originally thinking about. For this, a diode can be used, which is to be connected to a capacitive voltage divider, where the lower point of the flying capacitor is clamped at the half of the DC link voltage. Okay. All right. Gotta make sure I don't lose focus here. What are the S lines? Are those the sensing lines? These, do I have to measure voltage at those points? Because if so, this may not work. I'm confused. T27 creates an overvoltage spike at turnoff. I like the Zener diode here. Oh yeah, that's add a Zener diode. In series with DF. The Zener diode should be higher than the spike of turn off. This can be... Or you can use a current limiting resistor. I am still confused. This kind of makes sense that you want pull current that's flowing into the top one and give it to the bottom one. But how? Ugh. All right. Let me pull this. Look at this schematic again. Keep this off to the side over here. And look at this thing again. Okay, so in mode 1, both these are off. So I'm assuming not connected. So voltage flows in, or current flows in, up through both of those. It charges both capacitors on the output. So that's normal, everything's charging. Then, turn T27 on. What happens? How's it going, Beth? I'm just trying to figure out this whole system. All right. So 25 is off, but 27 is on. Flows in there. What happens? Voltage starts decreasing. Voltage increases. I don't think this circuit is working the same way as... not to say that it's definitely not working the same way as what I had originally envisioned. At least not in a way that is easy to understand. And if you turn them both on, it's increasing. I think voltage starts decreasing. All right. I'm going to try something else. Yeah, that's a video. Here's a patent application for it. That's funny. Okay, here's another random forum. As much as you can, I don't know how much you can randomly trust forums, but single cells are wired parallel, make discussion easier. We can concentrate on the balancing requirements of cells wired in series. Connected battery of 3, 1860. Means to balance the state of charge. If we liken this to 3 bucks. For lithium ion cell. So why should cells with very similar capacitor ratings ever come? Cells with the most charge into resistive loads and simply generate heat. This does not appeal to me. Active balancing is a term. Fine capacitors are as big as you like. 100 farads would be good. The potential difference between two cells will be small. Consequently, inrush current will be small. However, a low 0 ohm resistors will do no harm. The relay is simply tick-tock back and forth, continually probing, probably in anti-phase. When the cells are balanced, there is no current flow between them. Is anyone using this approach? Interesting stuff. This is in relation to solar energy, apparently, so. Shown below. Okay, so they're basically saying put a small resistor on the capacitor. They don't tell how to pick the values, though. That part is going to elude me for forever. However, I think if with the right like there's a way you set up the timer to have a 50% duty cycle. If you, I think it's based on values of capacitors and resistors. And in that case, you can just change those values if something needs to go slower or faster or whatnot. Let's see. basically everybody's saying maybe, but there's certain considerations that have to be made. And this seems to be and then I found a paper on this too, which went into some equations here on like what's going on. Oh man, really wasn't expecting to do any calculus tonight. I think they simulated all this though, so they didn't really do it in practice. I think the answer here is I just go for it and probably use a big like can capacitor type just in case. And then I don't know, see what happens, you know? Whoops. And then just use switches. All right, let's see if we can find something here. Switches, interface. Switches, RF switches. Power distribution switches, maybe? This might be not what I'm looking for. Could probably just do this with a, like, honestly, like a MOSFET or something, but see if we can get a through hole part. That's even an option. All right, not many left. Kind of expensive. I'm more curious just what these are and what they do. This might just be a waste of me looking into something random. In, out, out, out. What? Turns on power switch, ground, input voltage, current logic. Low power switch output. So what's the logic here? Power switch is an N-channel MOSFET with a maximum on-state resistance of 50 megohms. Configured as a high-side switch, the power switch prevents current flow from out to in and into out when disabled. So all it does is connect it, which is kind of what we want. I was hoping for one that would switch back and forth. Alright, but that shows that we're at least in the right neighborhood, I think. Parallel, serial. I probably want on-off interface. Are these all Texas Instruments things? What is this? Ground, common voltage. Goes high. I really don't understand what I'm doing here, and that's the problem. My problem is I don't understand enough about MOSFETs, like specifically how they work, and that's, I think, causing the issue. If I knew that, I could understand this a little better. I'll search electronic switch. What comes up? Toggle switches sound cool. But I don't want the. I obviously don't want anything mechanical. I want something that's electronically controlled. All right, what do we got going on here? Kind of. SPST. I want SPDT, right? Is that what I'm looking for? want a single pole double throw. Or actually a double pole double throw, I think is the best option, right? Yeah. So DPDT. Nice. Nothing easy to use. I could probably search again and find something better, but let me just make sure this is like at least in the realm of what I want. Ah, yes, it is. Okay. NH NCNO. Okay. That's a 3.3 volt system. I don't know what the maximum voltage is that can come through these pins though, because that does matter. And the commons would be connected to the capacitor. So this is a really good part, like for what we need. So this is in analog switches, multiplexers, demultiplexers. What's the difference between this and logic? In stock, active. Do we have any through hole parts? We do. Okay. Let's see, bilateral switch. What is this? A really old data sheet, or a horribly scanned in one. Sheesh. In, out, in. Wow. How old is this part? Let's look at something else. It's actually readable. This is probably really old too, actually. SN74 type parts. Come on. Oh. D0, D45, and then ABC. This is just a straight multiplexer. Yeah, that makes sense. So, not really what we want. So yeah, I think logic is not the way we're going here. Analog. Active. DPDT. Anything that we can use here. Not really. MSOP parts are great when you want to save some space, but they are not easy to work with when you're soldering by hand. All right, let's clear that. Let's see if just what through hole options are available. Maybe we can come up with something. All right, what's available here? Double pole single throw. Let's try these. What does this give us? Wow, these are expensive. I feel like I'm definitely not looking for the right thing here. Oh, yeah. Oh, wait, which one is this? DG 303, BDJ 3. 300, 301, 303. That's this one. Yeah, I think that's really it. That was 8. What's an SP4T? Whatever it is, it's definitely cheaper. Sorry, we can't find your page. Try again. Nope. Oh, that's not from Rochester. Okay. Let's try this one. Wow, a $10 part. Never easy to understand. I don't know if I'm just tired or what. If that's what's making it so hard, difficult for me to figure out what's good. Is this just a multiplexer? It does just look like that, doesn't it? Which makes sense. I mean, that's exactly what we're doing here. I just... We could use a multiplexer. We just have to connect things in the right way. Probably. I just really want a double throw switch. And that is apparently really hard to find in a cheap and easy to use package. I want a 2-to-1 channel. What do we say here? In stock, active. I think the hot weather does make us all tired. I was working outside for a little bit today, in a parking lot, for a couple hours, and it was so hot out. All right, we want a 2-to-1, like definitely. So let's start with that, and then maybe it's possible to get something with 2 circuits. Okay. They are expensive. Why? Like, oh my goodness. $3 for something like this. It does exactly what I need it to, though. Oh, wow. on resistance is still pretty high. It might be worth buying this part just because it actually does do the thing I need it to do. C is configured as a phase reversal switch and optimized for high-speed applications such as chopper amplifiers. It operates from dual supplies. Analog switch. Maybe I'm looking for the wrong thing here. Let's go back. Hold on. I need to go way back. To the logic, signal switches and whatnot. Okay. In stock, active. And then we want through hole. That will severely lower options. And then we want a 1 to 2. Two times 1 to 4. 4 times 2 to 1. Sure, why not? All right, let's go for price. And I want minimum quantity. So I want these to come in a tube. All right. Please find the datasheet. Hey. Two A, 2B, 2Y. Okay. A or B. This works. This thing works right here. It's obviously bigger than we need it to be, but it does the thing we need it to. So G is the active low. I guess that's the ground or like enable or something. Is there a pin table? I just want to know what that's called. Anyways, pull the G low to turn on the circuit, as you can see here. And then toggle A or B by flipping that line, and then it connects. Alright, but this just connects through logic. It doesn't actually physically connect the lines, which is what I need. Alright. Because this just passes logic through. I need it to pass the actual voltage through. So this is getting to the point to where I'm kind of coming to the realization that the way I can do this might be just to use a couple of inverters and then a bunch of FETs to connect them. There would have to be 4 MOSFETs per series circuit, so 8 total. This is getting ridiculous. We might actually just burn off more power by... Oh, man. This is where those actual like sensing chips are starting to become more like ideal, I guess. as complicated as they are to use. Oh, but you still have to sense voltage with them and control them. I think. Zero in stock, but I did look at this particular part for some reason. Let's look at that again, actually. What did this do? Can't find it. Oh yeah, it was used with this big control device because you had to sense and everything. Yeah, it was basically gonna become impossible to use. So just to get an idea, what does this look like? Boost mode battery charger with cell balancing for USB input. Are you kidding me? This is a switch that is basically supposed to do everything that I was trying to do. Almost. 1 amp charge. Man, I wish I known this existed. A lot to this particular part, but it does that whole circuit for me. Interesting. Or I'm sure it would have. Where's that circuit? Set. Current limiting resistor. The resistor value determines the cell balancing current. Amps for cell balancing. So this is probably used for like laptops or cell phones or something. Anything that has a dual cell battery. Interesting. Very interesting. Can provide 2.2 amps of charge current. Jeez. Ugh. All right, well, this isn't going to work for me. Yeah, I still have to do it myself. All right. I might just... Dang it. I thought for sure I could find something that could do this. And I think maybe... I still think I probably can. It's just either difficult to use or too expensive, or I just don't know enough about what I'm looking for. Back to these analog switches. What does this thing do? This is just an on-off. I think that's the main problem is I can't... they're only on-off. I guess if you get a 4-channel one of these for each, you could probably kind of do something. Oh yeah, 2 4-channels could do it. All right, hold on. In stock, active, and then I want a through hole part. Okay. So if I get single pole, single throw switches, but I get enough of them, I can make up a circuit that will work. Excuse me. All of these, even with how many pins they are just one. Okay. Let's see. If I go back here and I say I want 2 to 1, let's start with that. With 4 channels, right? What does that give us? These big Maxim chips that are like, oh, they're so expensive. Oh, we can't be doing that. I might have to just go for multiple chips here. How about 2 circuits? Jeez, these are still really expensive. Yeah, $3 minimum, jeez. Is this the one I just looked at? Yeah, this is that weird one. That phase reversal thing. Or I didn't fully understand like the resistance thing. X connected to Y. Yeah, this is not gonna work. I was premature when I said that earlier. Let's just go down the list a little bit. What was this one? I'm gonna end up having to buy like an expensive chip to do this. Okay, this is 2. So I would need 4 of them. Because I need 8 circuits. If I go here and say 3, how many do I have? Oh wow, these are cheap. I only need 3 of them. These are clearly all used for something, some sort of specific application, though, that I'm not understanding. Right. CD4053. Oh, that's this one. Okay. Oh, that's pretty close to what I want. I can get away with a couple of them. I just don't know if the internal resistance will cause a problem here. Logic, data, control signals. Applications. Factory automation, televisions, appliances, consumer audio, programmable logic circuits, sensors. Sure. Let's go with this. I'll probably end up using these anyway, just because. So the 4053B, AYAX. I need to understand the logic table, if there's one. I'm going to end up going through this whole stream without doing hardly anything just because I spent the whole time researching and learning. That happens sometimes. Where's the pin out? Oh, this looks like, so the way I was reading this, it looks like it connected things, but it actually just disables them. Hold on, I can't read this. AX or AY. Oh, this CD 4052B could be really useful though. Oh, I'm looking at the wrong table anyway. Okay. There's so much data. I understand why they do this, why they do data sheets that cover multiple parts, because they are similar parts and you can do that fairly easily, but it does make it hard to read when you're trying to scroll up and down, and you have to keep looking at different tables to find the table that talks about your specific part. It's table 1. Oh. Well, this is what I wanted. Connects BX, BY, connects AX or AY. connects them to what? The common? ABC. ABC. Okay, so okay. So once again, two of these chips would work. It's just the naming scheme is so weird. Okay, I'm starting to see how this works though. Man. Negative power input. This bothers me because of the way this is analog, this might require some sort of like positive minus or negative power input thing, and kind of like a op amp or something like that, which I don't know if that's going to make this easy to use. Let's see. Off resistance for DDD minus VE is 18 volts. Can I just connect VEE to ground? I'm looking for some sort of electrical characteristic that'll tell me, like, what the expected input is for this. VEE equals VSS. I think that works. Man, this is going to fail horrendously. This is for an analog, like, okay. The reason this is so hard is because it's for an analog signal. It's not for, like, power control, for sending current through. I'll keep this open because this part might prove to be useful, but I think I need to try again from the beginning. Power distribution switches. Let's try this. All right. Are there any through-hole options? Okay. So the way these work is going to be kind of weird. These are basically just going to be FETs or transistors of some type inside of a package. And they might be kind of expensive because of let's see, tube or tray, I guess, would be okay as well. how does this work? Please find the datasheet. Hang on. I'm just looking at something else to try and fix. So this isn't really going to work either because I need power to flow in both directions, which it's not going to do here. Ugh. Oh. Yeah, I don't think this is going to do it either. I'm trying to figure out. The article I'm looking at, this flying capacitor thing is used a lot for power boosting or inverting. So it's not super. The operation is weird, but the switches they use should be make sense. I'm just trying to find some article that just gives an idea of what switch they are using. Not there yet. I'm gonna have to take another break here soon. I know I don't stream for a very long time when I do, but especially after a full day of work, my brain wears out really fast. I get when I'm trying to figure this much stuff out. All right, yeah. I'm gonna have to take a break for tonight and think through this. Maybe I can talk to somebody about it and figure out what's going on. I need to kind of absorb everything that I've learned tonight and then try this again with a better understanding. All right, well, thank you all for joining me tonight. I really appreciate it. Hopefully, I wish I could have made it farther, but sometimes this happens. I just get lost in it, and it's hard to make progress sometimes, so... give me just a second here. Weird, okay. Well, I'll work on this more some other time. But thank you all for joining me tonight. I'll see you again Tuesday. I'll think about this some more, and maybe I can figure out exactly what I'm missing here. I'm not asking the right question or something. I'm just not really sure what switch to use, and I feel like it's a very simple answer. That's why it's hard for me to find an answer, because it's such a simple answer that no one's asked the question. So, or something like that. That happens a lot too. All right. I will see you all later.